Hello class, welcome to our lesson today dealing with section 6.7. This is taking normal distributions and using it as an approximation for binomial distributions that we've dealt with earlier in the semester. So there's some rules that we have to make sure we follow in order to use this idea. First off, this goes back to the N, P, and Q idea. So N is the sample size, P is the probability of success, Q is the probability of failure. The most important thing before we start doing this is you have to make sure that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. Basically, just take the smaller of q and p, and whichever one's the smaller one, multiply that by the sample size. As long as those are bigger than 5, we can use the requirement, or we can use the ideas because it meets the requirements for the binomial distribution. The normal approximation will use the following information. This information is the same as what we dealt with binomial. Notice this is the expected value or the mean, which is n times p. And then sigma, which is the standard deviation, is the square root of n times p times q. Those things are similar to what we dealt with earlier in the semester in chapter 5 when it came to binomial distributions. The problem with binomial distributions with using a normal type idea with the z-score table is that binomial distributions are discrete, so they're whole numbers, like number of tails tossed, so 1, 2, 3, 4, for example. Whereas a normal distribution, the curve is a continuous curve. And so we have to do what's called a continuity correction. And this will basically just shift over a little bit to make sure that we guarantee that our number that we want is included, and everything that would round to that would be included. So this chart might be a little hard to read in its current format. It's in your textbook, so if you want an easier version of it to look at. Basically what we have to do is we have to move the needle a little bit, one way or the other, by a factor of a half. Okay, so if the value is x equals 8, if we want at least 8, that would include 8 and above. Notice here, at least 8, 8 would be right here, but I moved it back to 7.5. Basically what we're saying is what's the lowest value that would round to 8 that would be included, and that would be 7.5. Notice here if we change it to more than 8, it's everything to the right of 8, but it has to be not including 8. So we have to move to 8.5 because everything below 8.5 would have rounded down to 8, and I don't want to include that. So that would mean I go from 8.5 all the way to the end. At most 8 would be everything up to 8, including it. So since it includes 8, I got to shift it over a little bit to 8.5 to make sure that it covers that. And that would be everything from 8.5 downward. Fewer than 8, I don't want to include 8, so I would go below 8, which would be at 7.5, and I go everything below that. Probably the easiest one to deal with long term, even though it's more work, is the one that says exactly 8. And to do the the continuity correction, I would just go half both directions. So it's basically saying what numbers round to 8 essentially, and it's from 7.5 to 8.5. We don't have to worry about the equal to piece, so like technically 8.5 rounds up to 9. Okay, because of the continuous nature of the normal distribution, we're not going to have to worry about that as we're solving any of those questions. Honestly, the biggest piece about this lesson is to make sure that we're on the right track in terms of this correction idea. We have to do that anytime it's a binomial case. So anytime we have this NPQ idea, probability of success and failure, you're going to have to do this correction idea to use the z-score table in order to be successful. A few examples here. The given values are discrete. Use the continuity correction to describe the region that's being found. And so if we want at least 2 classes absent, okay, so here's the number 2. I want greater than, okay, or equal to, so it's area to the right. But I have to shift this over a half to the left to 1.5 because I want to include 2. If it said more than 2, I would have shifted to the right and it would have been at 2.5. Probability no more than 14, I want to include 14, so it's no more than that, so it also includes that. And so I got to shift everything over to the right slightly because I want area to the left. And so I need to move the number over to 14.5 to guarantee that I've included 14 into my answer. If it said less than 14, I would shift it to the left instead of to the right. Exactly 12 is actually the easiest version. You just go both directions, so it's from 11.5 to 12.5. And then we'll go and see how to find some of those answers as we're looking at how to find the z-score and then how to find the probabilities. Okay, so here's an example of one. This says a food company delivers surveys in the mail. They send it out to 25,000 people. That's N. Probability or percentage you get back is 6%. That's P. Find the probability of getting less than 1,200 responses back. Now the issue is with binomial distributions, it can take a long time depending on your calculator and application. So the continuity correction it fixes some of that so we can continue to use the z-score table. So first thing is to check n times p and n times q. If I do n times p, 25,000 times 0.06, I get 1,500. That's higher than 5. If I do 25,000 times 0.94, which is q, that'll also be above 5, so we can use this idea. First step I always do is figure out what the mean and standard deviation are. So n times p is 1,500. N times p times q square rooted would be about 37.5, 37.55. I would definitely go to 2 or 3 places there. It might be better actually go to 3 places. I went to 2 here. It shouldn't matter too much depending on the scenario, but you may find it better to go to the 3rd place as opposed to the 2nd to make sure your answer's rounded correctly. Because I want x to be less than 1,200, I can't use x as 1,200. Now sometimes you'll get the right probability, but your answer for your z-score is technically wrong. So pay attention to that idea. Since I don't want to include 1,200, I want less than, I need to move everything half smaller than that. So that makes it 1199.5. That's my x value that I use because I'm on a continuous scale versus a discrete scale. 1199.5 minus 1,500 divided by 37.55 will be -8. Once I have that -8, I want a probability that's less than that because my question was a less than question. So I look for the z-score of -8. Less than would be 0.0001. It's very unlikely I'll get less than that response back because my average was 1,500 and my standard deviation is only 37. So it's highly likely I'll get more than that back. That's what that's saying. Same information, I want to get at least 1,300 responses back. Now 1,300 is my cutoff, but I want area to the right because it's an at least or greater than question. So I shift this down just slightly to make sure I include 1,300. So that makes it 1299.5. That's my x value. Minus the mean and standard deviation from the last slide, minus 1,500, and then divide by 37.55. I get a z-score of -5.34. I want greater than here, so my z-score value was 0.0001, but I have to do 1 minus that because I want area to the right. And it's highly likely that it's going to be the case where I get at least that many responses back. You'll notice my picture isn't correct at all. I just draw this to give a basic understanding. If I was drawing this picture correctly, my 1,300 would be way over here because it's way less than the average of 1,500. And so 1,300 would be way over here, and the area to the right would be almost all of it, 9999 as a decimal. That was a lot of information about the continuity correction. It's important for your homework and for your upcoming tests that you're able to do that idea. So you want to make sure that you're able to go back and forth. Should I go half above, half below? Should it be between? Okay, what should my x value be? And then from there, everything should be the same as what you did with things like the central limit theorem and finding z-scores based upon the mean, the standard deviation, and the data point. Make sure you're paying attention to that as you look at your homework, and then we'll continue to look at a few more of these questions in our next lesson. Have a good day, everyone.